This workshop will provide a comprehensive introduction to large language models, covering their capabilities, structure, and practical applications. Participants will learn prompt engineering techniques, retrieval-augmented generation, agentic AI design, fine-tuning strategies, and model evaluation methods. The session will conclude with a discussion on the future of AI-powered reasoning machines. And as a reminder, please hold questions towards the end of the session. Thank you so much, and without further ado, I'll hand it over to John.
Let me get set up real quick. Okay, I think it's kicking in. All right, so today we're going to talk about LLM application development, all the stuff that she said. Quick introduction from me. Hi, I'm John Berryman. I got started in aerospace engineering, found out I loved the math, I loved the software, but I didn't like all the gadgets and stuff nearly as much as I like the generality of math and software. You can do anything with that. So I got into search technology, ended up writing a book on the topic, decided that was a ridiculous idea, never to do that again. Worked for GitHub, got a chance to build out search there and got a phenomenal opportunity to be one of the early engineers for GitHub Copilot. Wrote another book, saying I would never do that again. And at this point, I am an independent consultant at Arcturus Labs. Please check me out at arcturuslabs.com. So today is going to be pretty fast-paced. What you're getting ready to see is a 6-hour course that I've condensed down to a 3-hour course for a Haystack conference in a week that I've condensed down half again to a 90-minute course for you guys today. We're going to cover prompt engineering, RAG, agentic AI, evaluation, fine-tuning, and the future of LLMs. And if we got any extra time, I've shoved other like little goodies and stuff we can talk about. Obviously, questions as well at the end. And so, without further ado, let's just jump right into it. We start off with the basics of prompt engineering. And we talk about several techniques that we as a world have learned about these strange alien technologies, how to talk to these things, and how to convince them to do what we want them to do. The first thing we'll dig into is called few-shot learning. Now, shot means example. So a few shot is just a few examples. This technique was one of the earliest techniques introduced in this language models or few shot learners. And I think we'll try to get these slides up to you guys. Every time you see something that's underlined, that's a cool clickable link. I've got that throughout the talk. And the basic idea is of few shot learning is when you have the prompt, you give it several completions and let the LLM figure out the pattern and continue the pattern. So there's, it's kind of an interesting example. We're all so used today to ChatGPT and having a conversation with these models. The original models weren't these back and forth conversant agents. They were just document completion engines. So if I was to say to the model, and by say to the model, I mean submit the prompt, please translate this to Spanish. How are you doing today? Then what would be a likely response for a document completion model? For a human, you'd say, okay, well, ¿cómo estás? Or however you say it. I've lost my Spanish. But for a completion model, it says, oh, there's a pattern here. I'm translating stuff, and they really want me to like give them stuff to translate. So it continue with, where's the bathroom? What's your name? How, you know, it's going to do all stuff like this. And so that was one of the frustrations of using the original completion models that made them kind of unwieldy. And so when we were still wrapping our minds around this, we came up with, well, okay, few shots. These things are completion engines. They figure out a pattern and they follow it through. So if you simply give it a pattern, then you can use the continuation of that pattern to achieve whatever purpose that you want. In this example, we'll start a pattern of translating stuff. How are you doing today? ¿Cómo estás hoy? My name is John. Mi nombre es Juan. Can I have fries with that? And based on that, if you found that little scrap of paper on the ground and it was clipped off, how would you complete it? You'd be like, aha, I know what it's getting at. It wants me to actually make the translation for it. So originally, before we did all the fine-tuning to make these things into chat models, this is how you got work. out of the models. And it's still very useful because a lot of the times we take the models to places that they're not familiar with from reading the internet 5 times. There's still places that they're not familiar. So you can give them few shot examples like this and help them kind of get over that hump and learn things. But we started getting smarter. We realized that with a little fine-tuning, we can make these things act more like intuitively you would want them to act. And so it's kind of an intermediate step between completion models and the chat models we're also familiar with right now, were these things called instruct models, which basically said, all right, whatever the prompt comes in, my knee-jerk reaction as the model is to assume it's a request and try to make an answer. And just that extra little prior that everything is a request made it so that you could zero-shot things. You could say, please translate this to Spanish, how are you doing? And the completion would actually be kind of what you'd intuitively feel good about. Now, there was still a problem though, and we're still not to chat models yet. With the instruct models, there was still kind of a feeling of like, it wasn't a conversation yet. It was all, here's one request, I've given you my response, and there's no good delineation to tell the difference between, I'm the user speaking to the model and this is the model speaking back. Because internally, even though you're doing ChatGPT, internally it's just completing a transcript between 2 actors, the user and the assistant. So we still had to build it into the chat models that we're familiar with today. Another thing that we found out early on is that it really does the models good to take time to think. Initially, there was a paper that was on a slide that I cut out where basically we would take the completion models and get them into the mode of thinking deeply by giving them a sample problem and then giving them an example of thinking thoughtfully through it and solving it. Giving them another example. And that would actually make it where if you give them a problem, like this one, you would think deeply about it. If I was to ask you this problem really quickly, it takes an hour for 1 shirt to dry on the clothesline. How long does it take 3 shirts to dry? How long?
An hour.
You guys are so much smarter than completion models. The early models would do just a knee-jerk reaction, not think it through, and would often answer 3. But by giving them several examples of thinking through it, it allows the models to kind of chew on the ideas and spit out something that is more reasoned. So after giving it this few-shot example version, one thing that we figured out is like, you don't even have to give the few-shot examples. You can just say simply, hey, let's think step by step. And when you incept into the model that I need to be thinking step by step on this, you see what happens is it actually generates a step-by-step process that allows it to come to better reasoning. Now, why is it so important for the models to have reasoning? Like, why can't they just quickly come to the right answer? What you have to know about these models is, and unfortunately in the longer one, I had a whole section of this. These models are predicting 1 token at a time. And every time they predict a token, it's the same amount of work they invest into the token. It's not like they think hard when it's a hard thing and they think soft when it's a soft thing. It's a chunk, 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 chunk. And they have no internal monologue. If I was to ask you this problem, without even helping it, you have little simulations popping up in your head to figure out how this stuff works. But these models, you see everything they think because it's 1 token at a time. So by giving them the example, the instruction to think out loud, you give them the ability to create their internal thought. And when it's time to say the final answer, instead of just attending to the question, they can attend to the question, their entire thought process, and then actually make a much more accurate version of the final answer. React is another super important developmental step in prompt engineering. Initially, I'm sorry, this is probably tiny. Initially, when you ask these models complicated questions, How many rooms are in the hotel that is home to the Cirque du Soleil show mystery? Then of course you get the knee-jerk reaction again. How can this possibly be a correct answer? Like maybe if they're lucky, they actually have that somewhere in their training data that is obvious to them. Maybe if they're super lucky, it's up to date. But more than likely, this falls into like what is information that cannot be known. So what React introduced was the notion of giving models tools to deal with. In this paper, it was just 3 really simple tools that give it the ability to search for a Wikipedia page, look up text within a Wikipedia page, and then finally to state I have the answer. It was just like I'm ending now, so that it would claim the final answer. And in the instructions for the model, remember there's no system messages at this point, but in the prequel to the model that says here's what you're supposed to do, they said kind of follow this process. Think about the problem, choose to act by getting one of those functions, and then observe the answer, and then just do that for a while until you feel like quitting. But what happened is it actually was much more accurate at thinking through the problem and going out to reality and getting the information it needed. If you ask it for the hotel, the number of rooms the question asked before, it will look up Cirque du Soleil, the show mystery. It's found out that it's not quite the right answer, so there's like an error message that gets promoted to the large language model so it can understand how to correct itself. Looks again, finds out which hotel it is, looks at that hotel, and then finds out the up-to-date information inside Wikipedia. So it's much more accurate. So this addressed a lot of problems, not completely, but it was the start of tons of things for prompt engineering and for LLM application development. Hallucination, obviously, was a really big problem. Like if you ask these models just to give you an answer, they are completely confident in giving you something that sounds right but has no bearing on reality. So this was the start of actually grounding the models to truth. It also heavily influenced the path of AI developments over the past 4 years. Almost all LLM models now are fine-tuned to use tools. They can go out into the real world and grab stuff. Anytime you ask the model or allow the model to reach out into the real world and pull something back in to have reference to it, that's RAG. That's retrieval-augmented generation. And this whole loop of think, act on it, observe the results, and just do that again and again, that is the core of agentic AI. So each of these 3 things that are ideas that we're going to be investing in quite a bit today. Super important paper. The next one and the last one we'll cover for today, it's a little bit truncated, is tree of thought. And so basically what this is you give the model a problem that is too hard to directly navigate to the answer. And instead you say, okay, your problem is not to get to the answer. Your problem is to figure out how one should get to the answer. And you basically coach the thing into creating a tree of possibilities, getting towards the answer, and then you effectively use like an A-star search to say navigate the tree and go as far as you can. If you reach a dead end, back up and find the next best path to get towards the best solution possible. These models, or this approach has become very important because it's kind of serves as a pattern for all the interesting reasoning work that we've seen come up lately. Now, what used to be an LLM application that's wrapped around the LLM itself is now basically being trained into the model so that they can kind of think through a problem, taste it for themselves, back up, re-navigate to something else. Okay, so everything up until this point has been just kind of a menagerie of fun tricks that we could use historically and still currently. They're still very relevant today for improving the prompts and making better responses. But then there's the practical application of like, how do you take this information in a real world problem, shove it into a single prompt, and send that up to a large language model? Well, there's 4 steps, and this is a big chunk of what me and my co-author outlined in the book. First thing is you've got to figure out how to collect information that's relevant to the user. And I'm going to do an example from GitHub Copilot, how we did this for completions in Copilot. But you collect all the information. If you're doing a travel apps, like where are they interested in going? You know, what kind of behaviors are they interested in trying? Are they restaurants, stuff like that? For GitHub, completing code, it was things like, what is the current document that they're typing in? Actually, I'm gonna go ahead and show this. This is probably more relevant. Do it this way. For GitHub, it is, you know, what is the current document they're looking at? What are the open tabs that, you know, as humans, when we're working through code, we have tabs open because we're referring back to them. That might have relevant information. What is the path of the file? What are the other symbols that they are getting ready to type right now? These are all the big selection of possibly relevant information. Now, a lot of times you can't just dump everything in. There's good reason for that. We'll talk about that in a second. So you need to figure out what is the most relevant pieces of information. Score them. Figure out, like, you can either do this in tiers, like this, you know, this set of information must always be included. This set of information is optional if we have space, or you can do it kind of in scoring. So if you're doing like some sort of retrieval algorithm that has like a score that comes back with each of these pieces, you can say, you know, take, you know, from the top score down until we filled up the prompt and it's less relevant. For GitHub, we found that our ingredients, at least that I have listed here, got scored out basically this way. What we accounted for ourselves as the most important thing is the file path. I mean, obviously, intuitively, the document itself is going to be more important, but when you're thinking about packing information into a prompt, that one line that we ended up putting at the top of a file right here packs a lot of information about, you know, what is the context of the rest of this file. The next highest scoring thing was the current document itself. Obviously, if that didn't fit in the prompt, you're not going to make very good completions at all. If we have room after that, then there's the information that's in the open tabs. And that's not all the information. That is, we'll get to it in a second, that's just the pieces that are most relevant. And then the last bit, and this is unfortunately the thing that I was working on, but it's the least relevant, were the symbols. If you're typing out a symbol, understanding that signature definition is a piece of information, but a lot of times what we found out is it's information that is often already open in the tab around you, so it's probably already there. After you have all the information, you have it scored, you need to be able to figure out how to snippet the information. Rather than just puking all the information into the document and hoping that, you know, effectively your code intern here can like read it and understand what you're talking about, you need to figure out how to get just the piece of information that is most relevant from each of these sources and decorate it in such a way so that the final prompt, the document that you send to the LLM, makes sense. And finally, you assemble it. And so the way that these worked out for GitHub Copilot, let's talk about snippeting. Obviously, we have the full file right here, but our file path was like a little bitty snippet. We always stuck that at the top. This bit right here, even though it looks like it is in the file that the LLM is looking at, was actually snipped out of one of the neighboring tabs. We would use a moving window and find the most relevant pieces of information, and then we would put it in there with its path. That's a useful piece of information. And we would comment it out using the comments of whatever language we're in, which is also really relevant, because what we found out at Copilot is if you write bad code, if you started using the wrong the wrong comment signs, or if you use like misspellings or something like that, then the completion engine would see the pattern and be like, aha, we're a bad coder today. So it's very important to write good stuff. And finally, you assemble it, pack it as tight as you reasonably can, and send it off to the model. The core ideas here are that your token context window is limited at some point. And you want to pack the information in as tightly as possible and present it in a way that the LLM / your young developer friend would understand it. Just try to empathize with the model in that respect. All right, practical considerations. Do you really have to do all that stuff? Well, maybe not. In the early days of Copilot, completion context window was 2,048 tokens, which was often not even a full file. It was just nothing to work with. So we literally count every single token. It was into minutia. But these days, the context window is 100,000, and I'm going to have to update that because, like, I think OpenAI just released like a million token models. That's the standard now. Every week's another 10x. So maybe you don't have to worry about this, but maybe you do, because there are still costs. The longer a prompt is, then the larger latency for returning information to your users. And in some domains, that's critical. Like I had a client that was dealing with voice over IP type stuff, and you whatever you're doing with that has to come back immediately. Also, the cost is more. So if you're randomly tossing a million tokens every time you do any request, then you're going to be paying for that. Second, irrelevant content still is distracting to models, and it can pull them off course. So you need to kind of pare it down to what is the most important stuff for the model to see. And also, a million tokens is only a million tokens. Like if you really want to stick full books and stuff in there, you'll eventually run up against Windows again. You've got to handle that somehow. So this is still something relevant and worth thinking about when you build your own LLM application. All right, final tips for prompt engineering. Pretend that the LLM is your dumb mechanical human friend who happens to have read the internet and memorized most of it. This means help LLMs by giving them text that they're familiar with. They have seen tons of HTML. They have seen tons of markdown files. They've seen SEC reports. They've seen like tax documentation, legal documentation. They've seen all that stuff. If you can build a prompt that incorporates those motifs, those themes, then you don't have to tell the model about this new weird file format you have. Just figure out some way of incorporating stuff that it's familiar with. LLMs are not psychic, despite what my clients want them to be. If information is not in the training or somewhere in the prompt itself, then they don't know it. And there's a lot of cases where that will be the case. You're working with private information or real-time information. These are things that obviously the model will have no knowledge about. LLMs get distracted. So don't just shove all the information into the model just in case it might be useful, because it might actively distract the model. They, like me, they've got a little ADHD. If you look at the prompt and you can't make sense of it, the LLM is hopeless. Empathize with it and think about like how you would approach the problem and how you would create the instructions for this problem to give to someone else to solve. That will help a lot. And finally, models think better if you give them a chance to think out loud. Chain of thought reasoning is very helpful. And cool thing about this month and last is now the models are kind of doing that baked in. You'll see more and more of that because it is so useful. All right, chapter 2, retrieval-augmented generation.
I have a question.
One question, but we're going to try to do most of the questions at the end because this is a 4-hour
So
course.
the bottom line mechanism is this predictive statistical prediction of the next token, right? So regardless of what type of prompt approach we use, so they will all converge on that statistical mechanism of figuring out the distribution. So how does the prompting make a difference at that level?
At that level, it won't, because it is the same mechanical calculation for every single token. But effectively, it's what you're doing by prompting is crafting the priors so that the next token is, works with those priors. It's like, if I'm given everything in Spanish, then it's very likely the next token is going to be a Spanish token. If I create a sensible instruction set, then the next token is likely to be one token that is a sensible reply. If I create garbage, then it's likely to be garbage. So prompt crafting is everything. All right, so what is RAG? Like I said, LLMs are not psychic. There's a lot of information they're missing. Private content behind corporate walls, recent content like news and stuff. Like you can actually ask the models when is your last training date, and you can see when, at the date at which is really going to start lying to you. Real-time content like, information from travel or weather API, stuff like that. It's not in there. So that's why we introduce RAG. Retrieval-augmented generation gives the model a chance to reach out into the data set that they're missing, reach out into the real world, and when they use that information, it's going to improve the accuracy by reducing the hallucinations and grounding it on real-world information. And it increases kind of context awareness. They can see, whatever problem space they're dealing with. If you give them information from that problem space, they're going to have more sensible answers. But a key point that I always try to drive home when I'm talking about RAG is everyone says like RAG is if it's a thing, atomic thing. RAG is two different things. RAG is retrieval and generation. And if you can keep both things in your mind separately, then whenever RAG goes wrong, then you don't have to debug this monolithic black box. You can say, okay, well, what is actually the problem, and figure out which side it's on. All right, so the next little bit is kind of a blast from my past when I get to take off my LLM hat and put back on retrieval and search hat. There are two major forms of retrieval that are popular for RAG. Well, to be perfectly honest, there's one that's really popular for RAG and one that I'm going to advertise is underutilized, and you should be interested in it too. But I think you'll see. So semantic retrieval has become kind of the de facto standard for RAG. And there's good reason for this. It does an excellent job at searching documents by meaning. Whereas lexical retrieval, which I'll show you in a second, is like find documents that have these words. It's a lot cooler if I can look up monkey suit and find documents for gorilla costume, because it's the same thing, even though the words don't overlap. What semantic search is not so great for, especially when we get to larger and larger data sets, is efficiently filtering and sorting. Also, it doesn't do good when it can fail catastrophically when you're looking for specific things, like find me a movie with this phrase. It has to be gorilla suit or something. Or find new jargon terms that it wasn't trained, this model wasn't trained on. Or find part numbers, part IDs, stuff like that. That's where semantic retrieval is not so great. The ETL process to get information in involves a couple of steps. You take your documents, you chunk them into pieces, and for each piece, you provide it to an embedding model, get the vectors back. That goes into your vector store. And then at the query time, you're matching vectors to vectors, really. So you take the query, put it through the same embedding model, and match the vectors, get the nearest documents out, and that's basically how it works. So let's talk through those steps briefly. Embedding vectors is just a set of numbers that carries meaning of the item. It has these properties. If you have two objects that are close in meaning, gorilla suit, monkey costume, then their embedding vectors in high dimensional, 1000 whatever dimensional space are going to be kind of close together. But if you have, dress shoes, it's going to be over here. It's going to be somewhere far apart. So that's the two properties that embedding models have to have. Embedding models typically don't have a very large token token window for OpenAI models, it's 1,891 tokens. So that means you've got to chunk up your text in order to embed it and fit it into the database. So chunking. Chunking is the process of actually splitting these documents so that they fit into the token window. There's several ways to chunk, going from simplest to most complex. Simplest is basically just use a sliding window and convert each of these into embedding vectors. You run into some problems with just arbitrarily splitting your documents, as you might split the important idea in half. So a slightly more intelligent way of doing things is to recursively split the document. Just split it on titles, sections, stuff like that, until it's small enough to fit in your model. That guarantees, mostly, that you're not splitting important ideas in half. And a still better idea is contextual chunking, which is effectively you take the second idea and you also do some other summarization, some other technique for dumping more information that's relevant to how this chunk functions in the full document. That'll just help out the model and the embedding model as well. And finally, you've got to dump these vectors into retrieval engines. There's several options for specialized services that have become popular recently. They're so popular that all the old school stuff has started to kind of bolt on vector, and I think it's probably pretty good. And if you wanted to host it yourself or have it like on your phone or something, there's options for that as well. The typical offering for any of these vector storage solutions is to store the vectors, the original document, arbitrary metadata that you have associated with it, and then what you can do with it is you can find a nearest vector to your query vector, and then you can use the metadata to filter down to like a subset of the document. So find the most meaningful document near this space, but filtered by this particular business, something like that. All right, so now lexical retrieval. I think somewhat underutilized in RAG. It has a really good ability to match on words and phrases, really good at filtering. It still matches on meaning. It's what has powered large chunks of the internet for most of the internet's life. But it's not quite as good as the vector search about finding meaning. And just to give you an idea internally how this works, whereas an embedding model takes text and turns it into a big vector, lexical retrieval takes the original source text, the quick ground fox at the top, and it goes through a set of steps to turn it into tokens. Lowercase is everything. It removes all the common words that don't have much meaning, because remember, we're using the words to imply meaning. And it takes the ends off of words. So jumped becomes just jump, so that that token matches any tense of that verb. And if we do that processing for all the documents that we're going to index, then we end up with document 43 represents the document that we're just talking about. We have a bunch of tokens per document, and we invert the index by taking all these tokens and using them as keys that point to a list of all the documents that they contain, that they're contained within. So this means that when you're doing a search using lexical search, it's kind of pre-done for you. If I wanted to find all documents about a fox, then I go to that key, and then there's the list. The search has already been figured out during that indexing time. And you can even do stuff, really quick queries for like Boolean stuff. Brown and fox, I just take those two vectors, find all the documents that are in both, and then send those back. And or would be doing the union of those two sets. Lexical search also has some cool things, cool tricks that semantic search does not have. For one thing, you can aggregate information. So since we have a quick list of all the documents that match our query, we can create counts and other aggregations over the information that are in those. This is useful information to provide back to the LLM. You can give the LLM the ability to see not only the matches, but to have an understanding about what other matches could be hiding there, kind of neighboring the original search. And We have snippets. We have the ability to pull out just the relevant pieces of the text. So think about this as kind of as a search time version of chunking, just pulling out the relevant piece of the text. But in my opinion, there is a big catch when deciding between semantic versus lexical search. With semantic, you can match a meaning, and honestly, it does a really good job most of the time. It fails with, particular words that are like jargon terms and stuff like that, and it fails catastrophically. That's unfortunate, but a lot of times it really feels good. Lexical search is really good with filtering, super fast with giant data sets. It's actually a lot easier to change the relevance and move around the way things come back. But the drawbacks for both of these are kind of the inverse. Semantic is not great on filtering, can't do any of these extra tricks. Lexical, it's searching based on meaning, but it's a naive, this bag of words style meaning. So there are, I won't get into them today for sake of time, but there are glimmers of hope about combining the best of both worlds. But it's still kind of, in my opinion, something that needs a lot more research. All right, RAG is two things. It's retrieval and it's LLM prompt crafting stuff. So let's look at the LLM prompt crafting stuff. This is also going to be a good demonstration of tool calling, because all RAG is, it's search on this side, and the LLM just does a tool call to get out to the information it needs. All right, so let's see. Is that halfway legible? Okay, some nods. I apologize if it's not. I'm going to see into. All right, it's doing its thing. While it's doing its thing, I'll show you what the thing of which it is doing. All right, so just a quick run through about how this works. RAG is two things. It's retrieval and it's tool calling in this case. The retrieval, I apologize, I faked it out. So here's a retrieval engine. If you search for very specifically anything with a title, then it'll just give you these hard-coded results. If you search for a movie that's about something, it'll give you these results. Effectively, what I'm doing here is emulating lexical search, exact match, and semantic search. But hard-coded, pretty boring stuff. This is the schema for that function. This is exactly what we have to give OpenAI's API, or it's pretty standardized across a lot of LLMs right now. And we say that there is this search movies function. We tell it what it does, and it's important to be fairly descriptive here because this appears inside the LLM's prompt internally so that it understands how to use it. We tell it the arguments that it can use, and again, there's the description. It's very important to be as descriptive as reasonably possible with that. And then we actually implement our LLM application. Super simple. It's not a chat bot. I'm just going to take one input, a user's request, and return a response, and we'll see how it behaves in certain situations. The user is going to supply a message, that's what they're looking for. We have an LLM call here, which takes this input. First, we have a system message that says, "You are a helpful assistant," because that's how you're supposed to start all these things. "You are a helpful assistant that can search for movies based on title description. If you can't find a movie, just say so." And then we just say what the user's message is. Then we do the model call. There's not, this is pretty dull stuff. We say, here's the schema that you can use. For the tools, here is the user's message. We get out the response. Now the response, and this is OpenAI, but this is fairly typical of other providers as well. The response might have tool calls inside of it. If it does, we say, "Oh, I'm going to print stuff out," so we'll see it on the screen in a little bit. And we say, okay, if there's a tool call, then for each of the tool calls, because it can call more than one, we're going to get the tool call out, actually send that information to the real function behind the scenes, That's us reaching out into the real world, and then we're going to send the information back to the prompt, the model. It gets added to these messages each time. And once the prompt has all the tool calls there, then it has a final response where it says, okay, I've seen my priorities, I've seen your message, I've seen myself, I've watched myself do a tool call, I've seen the answers come back, and now I can say whatever I want to say to you. All right, so let's run this through 4 different tests to see how this very, very simple application runs. Test number 1. We're going to say, do you have any good gunslinger movies? So this is its internal chatter to itself. It's going to say, I need to call search movies. And it actually correctly calls, it's something about gunslinger. Okay, so that's a good call. And we faked out the back end, and it's only returning whatever we had there. But a real RAG application would have probably semantic search that goes away and figures that out and returns something. Now the model sees all 3 of these things and its system message, which is hidden from us, and it knows enough information to say, here are some good movies for you. It takes this really messy data result and prints it into something that is going to be useful to our users. Pretty easy to set this behavior up. I'm looking for a movie that has the best in the title, but I can't remember the rest of the title. Must have been a late night. I was out of good examples. So it does the search movie request again, but appropriately uses the different field because we described to the model what this tool is about and how you can use it, and returns similar style results. Good. All right, tell me a joke about a chicken. Okay, it's supposed to understand what the tool is for and what it's not for, so it shouldn't just brainlessly call it all the time. And it doesn't. Why does the chicken join a band? Because it had the drumsticks. Okay, it's not that good. And finally, I tell people it's useful if your functions can error out to actually tell your model that the function errored out. So in our real function, search movies, that is hitting our semantic search, if something is wrong, then it's going to tell us, it won't just say, raise an error that is understandable to the developer. It's going to reply an error as a string that is useful for the model. So the model tries to get movies without anything. The tool responds with an error, it says no criteria provided, and the assistant uses that to say, you need to say something or other. So it actually is still a good user experience, despite the fact that the function itself errored out. Key important thing though, 2 things. It's RAG, it's a retrieval, and it's generation. Don't worry about thinking about one thing as a whole. All right, agentic AI. For the sake of our next few minutes here, agentic AI is 2 things. It's conversational agency, the ability to kind of like work with your new buddy, ChatGPT or something like that on a task. Or it's workflow agency, where you basically set up a set of steps to have the model go away and just execute on the steps. The important thing here, there is a uniting factor in both of these, is, until we get to AGI, we really still need the human in the loop. The human is the kind of corrective function for both of these. With conversational agency, the human is going to redirect the conversation when the model kind of gets off. With workflow agency, the human is the person that creates the steps for the model to act on. And so in both cases, you still need to have a human in the loop. Conversational agency. The original no tools ChatGPT is actually kind of the simplest form of conversational agency. You tell it about yourself, you let it respond, you go back and forth. An agent has an environment to work in. And with no tools, an agent is still an agent, but it's constrained only to the world that's created in the text on the screen, right? So It's not able to actually see with sensors out into the world or hear what's happening or control things. But if we give it some tools, then the thing becomes potentially quite powerful. Its environment is not bounded by text anymore, but it's bounded by whatever you allow it to see out in the world and whatever you allow it to control out in the real world. So let's dig into that. Defining a conversational agent is easy. Effectively, it's just a set of instructions. Here's what you do. A set of tools, that is, it's sensors and actuators out in the world, and a loop. You just do it over and over. And probably I should put a user input. That's going to be important too. The system message, the instructions, describe the role of the agent, the purpose, what its tasks are. It describe, here is the environment that you're going to work in. You're a legal scholar, you're working in legal documents, you're a travel agent, something like that. It describes the behavior that it's supposed to use to interact with the users. Is it going to be really brief and precise? Is it going to be creative and fun? And also in the system message, especially for domains that are kind of particular, not common in training data of the internet, you can provide few-shot examples to say, you know, here are examples of things you might see. Here's good behavior for you to judge yourself by. And then you give tools. OpenAI AI recommends roughly like 20 or so max. Make sure the tools, similar to the system messages, have good distinct purposes. They need to be distinct from one another so that you don't get the model accidentally calling this one because it just sounds like it's that one. It's good to kind of partition the actions into different elements. If some of the arguments to the models can be enumerated, tell the model that helps it. And if you have to do like long form inputs to the arguments, you can do that, but it's not usually ideal. It's usually good to make it kind of like a function call. And then you have the loop. So let's see, what's the easiest way to describe this other than just looking at it? Basically, user comes in, says a message. Sometimes, if we don't have any tools worth playing with, the application, it sends that to the model, and the model skips all the way to the bottom and says, here's your answer. But it's a loop. It goes back up to the user again. The user says another message, and this time, when it goes to the model might say, well, I need to make a function call. Let's get the evaluation from that, stick that in the prompt. We can do that several times. You can do like function calls in parallel. There's kind of some nuance to that. But it builds up a longer history with every one of these inner loops, the tool calls, and every one of the outer loops. It's building up further and further context, and then finally it returns the response at the bottom. But not too complicated, right? I mean, these things are amazing, but it's actually not that hard. So let's build one real quick. Oops, that won't make that code work. What did I call this thing? Package. Okay, so Python chatbot. Beep, beep, beep. Okay, that's running, and it's going to let me actually talk to it this time. Chatbot is basically the same thing I just showed you, just with different tools, and I've got a loop on the outside. So I put it inside of a class. When you instantiate this conversation class, you can give it tools, so it's generic. You can make it a different type of agent. You give it a system message. Whenever the user says something, this is what gets called in the user loop. Then it does exactly what I showed you guys in the other one. It's just a little bit more complicated because instead of one hard-coded function, I ask it what function it needs, and I go grab that one and use it. But it's just that picture in the previous slide. It's not actually too much going on here. Inside the main method, I'll say, here are my tools. I have a get stock price, I have get weather, and I have get clothing recommendation for the weather. I'm sure it was a late night, and I just ran out of creativity. Here's the hard-coded implementations. To be cool, you would put match these up against real APIs. And here's the outer loop. Not much going on. While true, we're just going to take, the input from the user, say that the model, and it prints it out based on that. So let's try it out. See what it does. Is this making sense? I've got to go kind of fast, but it's okay. All right, user. You know what? What should I wear in Miami today? Because I'm going to Miami. Okay, so this is cool. We can see what it's doing. It sees this. It calls two things, fortunately. It says, well, what is the weather like in Miami? It's like this. And it says, I'm going to get a weather clothing recommendation. The weather is raining, so it calls it correctly. And then, this is all hard-coded responses, but you can imagine a real API returns that. At every step, the model is reading everything. It just keeps prepending it to it. And so now reading all of this, the model has all of it needs. It's a document completion engine internally. That's all it is. The model understands that it is supposed to write the assistant text next. And oh yeah, I forgot to tell you, the system message, it's a pirate. So R, in Miami today, it'd be raining with a temperature of 25. You best be wearing a raincoat to keep yourself dry, matey. Why did I do that? Is New York any better? All right. It does a similar tool call, and I'm not going to do the pirate voice again, but it responds about as you expect, and just because, give me Apple price today. Okay, I'm just using the final tool. All right, and it looks up that. So you see how easy it is. Now, back in the day when tool calling first started, like it would call the wrong tool. Sometimes it would get off track pretty easy, and it still does that. But things are getting a lot better, and they're just going to keep getting better. So we have this weird superpower where that's 191 lines on the screen. I've done some amazing stuff that I couldn't. There's just no way I could do something like that 3 years ago, 4 years ago, right? So really cool time we live in. Yeah, the only sad thing is I get to stand in front of a bunch of people and say, it's not that hard. It's like, I thought you were a consultant. I'm like, sorry. All right, this is my most favorite part of this section. I'm actually really into UI UX. I like the psychology, and I think it's really critical in working with these machines. So there's a cool thing called theory of mind that we all have, which is our ability to simulate what's in each other's heads and modify our behavior based on that. And when you're building a UI and a UX, you need to make sure that you allow your users to build up that theory of mind for what's in this artificial intelligence mind. And the way you do that is to let the user know what the model is looking at. You guys are teammates, and the model is attending to something in the real world. Make sure that the user sees your gaze and figures out where it's looking. So cursor, does anyone use cursor here? Does anyone use Copilot for code completion here? Okay, well, good. I use cursor. I remember I started saying I was a Copilot engineer. Don't tell anybody. Cursor's kind of nailed it down. And here's me basically bragging on them. They do a really good job about saying, as a model, here's what I'm going to look at. We're looking at the same thing now. You got these like little tokens, these little pillboxes so that I can see it, and further verification about what it's looking at. If you were to do something that requires a search, then initially it'll just show you just this line right here, but you can fold it open and you could say, I really want to understand how you came up with this answer. And you can actually introspect into the model's mind, what it's looking at. UI UX show what the model is thinking about, not just looking at. When the model starts creating an answer, then prompt the LLM to say, tell us what you're thinking about. Tell us how you're going to solve it. Now that you have, in your mind, solved it, tell us how you think it works. And this gives the user a much more comfortable understanding that they can backtrace in basically 3 different versions to figure out what really happened. It's also a really useful way to increase the chain of thought. by having the model describe things to the user. You're effectively having the model describe things to itself. I'm going to break your hearts, I hope. The best thing, the coolest, most interesting thing in my mind right now is work around artifacts. Whenever you're working with a project, and this is super relevant to software development, I am working with an agent on a thing, but it could be useful anywhere. I am working on writing a document. I am working on building a travel plans to some other city. Whenever you're working on a thing, in the current prevailing paradigm of a chat, you start chatting to it and it has a really good answer and you're like, man, I'm going to save that one, and it kind of scrolls off to the top of the screen and you're like, oh, let's modify it, let's do something different, and it'll like rewrite something, and it'll, now you have version 1, version 2 that are kind of scrolling off. I think the future of agents is going to have a distinction between talking about the work and the object of the work itself, which is the artifacts. Unfortunately, we don't have time to discuss it because I got 30 more minutes. So this is, if there's more time, I'd love to talk about that. I've got a fun blog post and demo for later. All right. Workflow agency. This was my introduction to workflows in 2023 when the LLM world was still really young. Sorry for the profanity, but Spencer Scott had this buddy that was basically using LLMs to spam a random list of Shopify storefront owners to say, hey, I've got a new product. And the wild thing is, like, they were answering, really engaged, and it was a lot higher hit rate than he was having himself for manually doing the same work, and it was scaled drastically. And the results, he would see some of the answers, some of the requests out to these users, and they were really cool. So there's a sock store, and the model, without reading the whole thing, it was pitching this idea of success stories where the customers get to put their faces on the wall next to their socks or something like that, which is a really cool idea. And I was just enamored with this idea, and I called these guys out, and I was like, can I use that for the book? And so I've got like a whole chapter on this random tweet. But it's easy. Basically, you take something that is a complicated idea, and you break it down into chunks where each chunk is manageable by a model. In this case, give me the text for the storefront, extract the relevant details, brainstorm an idea, compose a marketing email, send it. That's all there is to workflows. When creating a workflow, you define your goal, just like the example we had. We figure out how to break it down into specific smaller tasks with the idea that each task should be achievable with a fairly simple interaction, and it can't get too far off track. You implement the individual tasks and test them, hopefully in good isolation. That's kind of an ideal, and then you wire it together as a full workflow. The tasks should be small enough to be achievable. The inputs and outputs, ideally, are well defined so that you can describe these things as objectively as possible, and so that you can have them in isolation and only have to reason about one of these little boxes rather than this full box. Examples of tasks: you can have LLM-driven tasks, or you can have deterministic tasks. So for LLM tasks, you can summarize text, do entity extraction, classifying or routing if you have, kind of a fork in your workflow. But there's no reason that you have to use LLMs for every one of these steps. Deterministic things are important. You need to read the data from somewhere. You need to write it somewhere. You need to store it. There are modifications that you can make that don't involve actually, getting out an LLM. And once you have all these individual tasks, you combine them into the full pipeline. A really common pipeline would be just a chain. And this is how, how many of you guys have heard of a laying chain? Okay, good. That's how laying chain started. That's why it's called laying chain, because you could line these things up in a chain. But soon we found out that actually these things could be full DAGs. You can have a lot of behavior that's going on, which kind of thwarted LangChain a little bit, but I digress. You can even have cycles. It becomes more complicated, but you can say, like, if something is wrong with a marketing email, put it back to an earlier step and like try again with extra information about why it failed. But it obviously becomes more complicated because this step now has to understand the possibility that there was a failure in the history. So it's a little bit more complicated. What you've got to avoid is eventually running into stuff like this. I still, the models are getting better and better, and I'll show you in a little bit, able to do more and more work without you there holding their hands. But if at some point it becomes so complex that it's not worth it because you yourself cannot figure out what's going wrong if something breaks. This is just a reminder that in both of these cases, conversation and workflow, it is the human that is the secret ingredient. Human has to be there to keep the model on track, either by talking directly with the model about their work, or by setting up a workflow that keeps them, defines the Rails themselves. All right, demo time. This is our last demo. I made it. I made the Shopify emailer. I'm gonna be rich. CD. Who are you? DSPY. Python main. Let's move the screen a little bit clearer. All right. I've downloaded a bunch of storefronts. Fly by Jing. Let's see. That's a good one. It's are you familiar with it? You like their spices? It's a spice store. I'll have to try it then. Okay. First person I've talked to that knew what it was. All right, we're gonna run it and see what it tells them. Fortunately, I use DSPY and it caches everything, so it's super fast. Otherwise, this take about 30 seconds. Dear Flyby Jing, I hope this message finds you well. I have recently explored your vibrant store and was truly impressed by your commitment to quality and flavor, especially your James Beard Foundation, blah, 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 blah. It actually does a really good job. I've kind of prompted it to brag on them and then to tell about like this cool idea, a recipe plugin. So as soon as you buy something, you get recipes for stuff. And then, talk about like next steps. So not bad. Let's see actually how the thing works. That's this fellow right here. This is going to look different from the previous ones. I have opted to use DSPY, which how many people are familiar with that? It popped up for a bit and then it popped back down, right? It was kind of a cool framework where basically you think about what the steps are, and you think, the summarize a website step has inputs, which is the HTML, and has, in my case, outputs, like what are they selling, what principles do they intone, what, tone of the website, what's something that's praiseworthy, that's what we picked out with the James Beard Award. And so all we have is like, I think like just 3 steps. We summarize the HTML. When we ideate, it's actually kind of 2 sub-steps. We brainstorm all the cool ideas based on the summary. We ideate, which we pick out like whatever's the best one and augment it a little bit. And then we generate the actual email, which takes in the information from above and figures out what is the best, nice way of luring them to our storefront. And finally, we have something that combines all these steps into the work step. So I've done exactly what I showed in the previous slide. Come up with the steps, make them work in isolation, and then combine them all together as one. Ultimately, DSPY is a really cool way. It's actually for prompt optimization. You can actually say, here's input output that works. Just make these things better. But it also does a lot of hiding of the prompt, which I didn't like too much. But how do we get to that next, actually? We get to that here. So a big question for everybody, and honestly it's still a big question for myself, is what frameworks should I be using? A thing that a lot of people picked up early on is LangChain. But LangChain at this point I haven't heard a really nice thing said about it for about a year now. It makes a lot of things overcomplicated. It's easy to set up and get a demo going, and if you want to do actually something on your own, you've got to have a PhD in LangChain before you can get your own thing. They are trying to ease this situation with LangGraph. Importantly, instead of just a chain, which is one of the ways that LangChain broke, it says everything's a graph, which makes more sense for workflows. The SPY is what I just demonstrated. Llama Index has been around for about a year, and it's covering some of the same territory. You got your squiggly graph there, so that seems right. PyDantic, I'm interested in it, but I haven't touched it yet. It's written by the same guy that wrote PyDantic, but PyDantic AI. PyDantic has been used in everything for OpenAI, and all these libraries use PyDantic. So it made sense for PyDantic company itself to take a stab at this space. But what I'm finding a lot of people use, and what I honestly am still really attracted to myself, is just like grab the OpenAI like endpoints and just use them. The actual API is ridiculously simple, and it doesn't do any hiding of the prompt itself. So rather than investing in a workflow orchestrator thing that might have everything you want in 10 times what you actually want, that you have to debug eventually, a lot of people are still kind of going it alone and finding that it's a happy path. So my advice to you. All right, the big scary subject, evaluation of LLM applications. This one's challenging everyone right now. It all starts with vibe testing. You have your prompt template. It's a thing that makes stuff. What does it make? Well, it takes your context, which is like metal wire, and it makes an output, completions, which hopefully are springs. I actually looked up, that is a spring maker. That's what that machine is supposed to do. So vibe testing is what you just stick something in, make sure the machine is calibrated like you think it should be, write the prompt appropriately, and look at the outputs. But then you try something else, or worse yet, you put it in production and somebody tries something else, and there's your spring. You come out with a spring that's not a spring. It's like, ah, crap. So that's where you introduce a human expert. Now, several important aspects of our human here. This expert is the domain expert. It's not just an engineer. And if you have an engineer who is also a domain expert, then give them a pay raise. They're going to be really important. The expert has an understanding of how the prompt should work. They know that given this input, here's what the output should be. And they can be helpful for noticing problems as they arise, and diagnosing things and figuring out before you go to production what some of the problems are, because they know all the corner cases. But humans don't scale too well. That's why you introduce automated evaluation. With an automated test, the goal is to basically take this expert's understanding of how things should work and encode that into a machine that can automate it. If we can do this, then we can test the prompts offline before we ship them to production. We can test them in mass. We can sample prompts as they're working in production, and we can notice things a lot quicker than our human can. So let's talk about building and deploying the evaluations. Here are the ingredients and steps required for that. First off, you need the prompt that you are working with. You wonder how good it's going to work? You don't know. You need context. Lots of examples, different types of materials, different types, things that are going to trigger different behaviors in the large language model, different corner cases. And you have to have that good understanding of what good actually is. This is something that our expert gives us. Once you have these ingredients, then our expert, and probably with an engineer, can apply these into automated tests So we have all the nice, behaviors online and as we're shipping things into production. Once we have that, then we are able to set up all those testings around the sampling traffic, etc. So what does an automated test look like and how do you build it? First of all, let's look at the typical shape of an automated test. On the input, we have context, different types of stuff. And in this case, we're doing movie reviews, for an example. It was like watching paint dry, but somehow less exciting. The movie has tried to be deep, but it ended up being dull. It had me hooked from finish to start. So we have different contexts, and our prompt template, obviously simplified here, is going to be something that, in this case, figures out reviews, positive or negative. And then once you run each one of these pieces of context through the template, you have outputs. The first one is positive and the negative and good. First one is wrong because it got the sentiment opposite. Second one is right because it got the sentiment correct. And the third one is wrong because even though it got the sentiment correct, it used the wrong word. And so what you do, all this information is what you actually stick into the automated test. The automated test is not any individual one of these. The automated test is the thing that runs this entire suite and says, okay, well, today you have a 33% pass rate. There's two forms of automated tests. In the fuller version, I have like a third form, but it's effectively, I kind of lumped it together here. One thing is algorithmic tests. These are the fortunate things that you don't even need a large language model to figure out. With an algorithmic test, you're testing things that you can do in code. If you're doing structured data extraction, then you can have hotel websites, and then you can have known human curated examples of what the address and the name of the hotel is, stuff like that. If you're doing classification problems, then you can have sentiment analysis like we just did, and then you can have a known list of what the outputs should be. If you're routing workflows, then that's effectively just another type of classification, like go left or right in this workflow. And function calling, honestly, is just another type of classification. It's like classify according to which function that you use, and within the function calls, here's like how you should call them. And that you can imagine other things that you could automate, like if the response itself should be always of a certain size, that's easy. If it should be a bulleted markdown list, also easy. You can do things like that. So I'm not going to go into detail about an example of this because you can imagine it just takes the input, the output, and it's pretty easy to make Python that does any of these things. Is this the same as that? It's equivalence. Where things get really challenging is with LLM as judge. We are leaning into this more and more, and we have to. It's because right now we use humans to look at the more subjective feeling things. Humans scale, though, much more poorly than large language models. So we're really hoping that large language models are going to be able to do more and more of this subjective quality assessment work. Examples are like the quality of response. Does it capture the main points? And you can like list the points and then have the text. So you can still do kind of like this, here's my context, here's the expected output, but instead of like exact matching, you're doing like, does it at least hit these high level points? Harder response formatting. Is it going to be a paragraph and then, a list of steps? It's, you can do stuff like that. Hallucinations. Given this output, does it actually at least map back to facts that we learned from the input? Comparison. Is this output better than that output? Subjective quality. Is my assistant fun and helpful and friendly? Stuff like that. Creating an automated test is easy. You write Python that determines if the expected exactly equals the actual. Creating an LLM as judge eval is much more involved. And here's the 4 steps. You got to gather a lot of examples. You got to define your criteria. You got to write the LLM as judge prompt. And then that's not the end of it. it's going to lie to you. You've got to figure out how to align it to your actual expectations. Gathering examples. This can be hard too, right? If we're doing like the hotel structured data extraction, then we go online and get a bunch of websites for hotels, and we actually, manually pick out 30 or 40 examples. It could be something that doesn't exist online. We have to create that data synthetically. You can chat with an LLM and say, hey, here's a situation. We're going to put our users through this. Help me brainstorm all the different scenarios you can think of. Help, create these personas, these users, and for each Cartesian product in that space, figure out like a good example of them working through the product. And that'll be a good way of coming up with a lot of tests. You've got to read them because it could also still lie to you there. And then if you're lucky, or maybe unlucky, you can gather examples where this is already going through production. If it's broken in production, I guess you're unlucky, but that's another source. Next up is gathering the criteria. So whenever you're looking at trying to evaluate a user experience, then it's hard, like if you actually sit down and do it, it's kind of hard to come up with like, the model needs to be chippy. The model needs to be, it's really hard to come up with what the model should be doing. And there was an interesting paper, Who's Validating the Validators, that's directly about this, where they started looking at, as a user study effectively, they're looking at humans that are working through this process. And they found out that if they came in with an idea of how they would have the LLM as prompt work, as soon as they started looking at real data, they reassessed their approach and they're like, okay, no, this I can see like a whole genre. All these errors are categorized as this, and then we've got these 5 different categories of error. And so that made a big difference of just reading through the data and figuring it out themselves. Also, you can participate with an LLM, have a conversation with it, and brainstorm more ways of looking through the data and figuring out a good way of judging it. Now you've got to create the actual prompt itself. The ingredients for this are the context, the prompt template, the completions, and the desired behavior, and you stick this all into a prompt. The following is a transcript. We're going to judge blah, 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 and here is an example of the desired behavior. That's where you take this and plug it in up there. The user request is this thing, and we're going to take, basically that's our context, whatever information we pull in from the user, and stick it into the prompt. And here's the completion that happened from running that prompt. Now it is your job as the judge to figure out, however you want it to respond. Critical thing though, whenever you're using an LLM to implement an application, it can be flowery and creative and do whatever you want to. Whenever you're building an LLM as judge, make sure that that answer is yes or no, or maybe categorical, or God forbid if you have to, like ordinal numbers, but yes and no generally is better than that. Something though, so that you don't have to have yet another layer of like subjective, like, well, crap, this was its opinion, so we've got to make an LLM as judge of LLM as judge. Don't want that. And finally, just because you wrote this prompt doesn't mean it's actually going to align with a human's thoughts. You might have written it wrong. There might be examples that you need to include. So you align it. As a starting point, you have your expert labeled samples. And you have an LLM as judge prompt that you're going to provide the same context through. Step 1 is to run the LLM judgment on the same samples and record the outcome. Then, now you have the truth, supposedly, from the human, and you have the outcome from the LLM as judge, and you determine the alignment, accuracy, precision, whatever you want to use there. And next, based on that, you say, okay, well, that was good enough, that was not good enough. If you can have a human, this is kind of work intensive, if you have a human look at the examples and where they broke down, then you can understand the disagreements, clarify the prompt from the last slide, add some more few-shot examples to keep it on the right path. And there's even, like DSPY itself was a prompt optimizer. So there are techniques out there that you can automatically say, make this align as well with a human as possible. Go back to step 2, do this a few times, and then the most important step, give up. At some point, humans don't agree well themselves. So you shouldn't expect the model itself to agree better than inter-human agreement. The whole idea, the ideal is for the model to just tell you the truth. Practically speaking, the idea is to have the model put you directionally in the right path. You can run this for one day, make a change with your prompt, and then you can at least directionally say, this is obviously worse, obviously better. You can at least stay on the happy path. Actually physically implementing this need not be so complicated. A lot of times your human experts will be perfectly comfortable with spreadsheets. So give them a spreadsheet full of completions and have them judge it, and then have the model dump its completions in the same spot. And then you can just use Excel spreadsheet functions to figure out the accuracy, and then do a few generations of that, and you can see how your accuracy is changing over time. And so it doesn't have to be some sort of automated process. All right, different takeaway. LLM evaluation is still hard, and it's still not super accurate. We're wrapping our minds around it. Models are getting better, but they're challenging. So one thing I always try to see if we can do is sidestep a certain degree of evaluation, the unnecessary evaluation. If we can avoid some types of evaluation, we'll save a lot of time. And it's a common conversation I'll have with clients where it's like, they'll come to me and they'll be like, well, here's what we're doing. It's financial data, and we're 80% accurate, and then their eyeballs start sweating, and it's like, but it needs to be 100 or I go to jail. Don't build things that absolutely require, some obscene degree of accuracy if you don't have to. One thing that you can do is think through the user problem. The users don't want to be completely removed. They just want more visibility, and they want more efficiency in the work they do. So if you can build an application that saves user time, but hands over to them the visibility into the model outputs to understand what's happening, then you can offload a lot of the really finicky evaluation to whatever the user needs in real time, and they'll be super happy for it too. All right, fine tuning, and I don't know, should I just blow through this one, or should we stop for questions and pretend fine tuning doesn't exist? Okay, it's not very good though. All right, see, here's an example. When to use fine tuning? Rarely. Okay, fine tuning. GPT means generative pre-trained transformer. These things were trained to read the internet and just predict the next token. And because of fine tuning, we have all this cool stuff like chat models and tool calling and reasoning models, things that are much more comfortable to work with. And cool thing for us, we can also fine tune these things actually a little bit further and build even cooler applications. But it is at a cost. Fine tuning takes time and quite a bit of effort. You got to gather a lot of training data. A lot of time when you train it, you try to debug it, it's not always going to work. You must develop. That's a part of a sentence, and I wonder what the rest of it was. You got to do this over and over every time a new base model is released. It also doesn't always work. LoRa is the fine-tuning we use so that we don't have to do a full fine-tuning. Basically, we can fine-tune a small subset of the parameters. It's really good about inculcating new behavior into the model. It doesn't teach it anything new. It occasionally has this fun little quirk called catastrophic forgetting. I had a consultant friend that was building out a fine-tuned model to extract FAQs from documentation. And he fine-tuned a model for that. And it did a really good job until the text was longer than that. At which point it would start asking questions about gremlins, literally. It was nowhere in the training data.
Oh my God.
And it's like, what can you do? It's just broke. Fine-tuning drastically slows down the feedback loop. If you don't do fine-tuning, then you change the prompt, run it again, potentially on your 1,000 inputs, and the cycle is like, 5 minutes, 30 seconds. It's just not much. If fine-tuning is inside that loop, then it's a day or more of actually trying the fine-tuning, then seeing if it works, and then you got to go again. But there are times where it might be useful. One of the things that we used to say is it reduces the size of prompt because you don't have to, stick in all the directions or examples, which is true. But it's rarely true anymore. No, it's still true, but it's rarely useful anymore because the prompts are just giant. And prompt caching is available, which helps a lot. If you want to change the output structure and behavior and tone, you can do that as well. And that's actually still quite useful. And if you want to move the capabilities of the larger model into a smaller, cheaper, faster model, that's actually a really cool thing too. You can embed a model on your phone. That used to be a call out. But you also have to weigh it against the other option of waiting 2 months, which has been a pretty successful thing to do for the past 3 years. Performing fine-tuning. Got to collect your desired outcome, collect the training data, upload the data and train the model and use the model. And let's give a quick example. Basically, I changed the names, but I was working with a client who had a real estate app. And what it would do is the user would say, can you pull down the comp sheets for the real estate in this area? And it would give, you would read in the information from the tool, and it would put in text the information that it learned from the tool. But that's not what they wanted. I mean, it makes sense, but one thing cool you can do is if you could contort the model into actually just reiterating the tool response as if it's in place of that noun there, then they could take, the response and embed it into like a much prettier UI. You could do kind of cool things with that you can't do with text. But no matter how much they begged the model, it would only do it sometimes. But that sometimes it was actually useful. So basically what they did here, let's see. When you collect the data, what happened here was we could ask the model, we could give the model a bunch of examples, beg it to actually write the correct completion. It would do so, I don't know, maybe 10% of the time, but that's enough. You can actually scrape those results, and there's your training set. We have synthetic training data that's actually pretty legit. You can take this information, and I won't go over the details, but you can ball it up, send it up to OpenAI. It's not that hard. Basically, just take the conversations that demonstrate working, send that up to OpenAI, and train it. It's just creating a training job, and then after that, you can use the model that you've created as if it's your own GPT. So that's basically it. I have a bunch of cool stuff right here. It's other cool stuff right here, and then the end slide. Cool. So that's it. We have negative 1 minute for.
We can take a 30-minute break, so if there's questions, and that might be.
Okay, I'll stand up here and do stuff. If you
Can you say something about distillation?
about distillation. Distillation's interesting. So the models right now internally, rather than just predicting the next token, the next word, they're actually predicting the probability distribution over all possible tokens, 100,000 somewhat. And what they figured out pretty early on that you could do is rather than, you can take that information And rather than training a model just to predict that, that one token, you can train the model to predict the distribution of tokens. And it's a super fast way of training models. So you can take a really, really big giant model and grab the distributions for a bunch of inputs and then use that to train a significantly smaller model that just has to have the same input-output dimensions and stuff 90% of the knowledge of this model into that model. And it's a smaller, lower latency, all sorts of cool stuff like that. But for that reason, our big providers like OpenAI has limited the visibility into the probabilities. They used to show you, and they still do to some extent, but they've made it where it's a lot more tricky to actually distill a model on your own.
I'm an amateur, so sorry for a very basic question. Can you explain the link between tools and when you're in the RAG section and then like a store of documents, which is kind of what I thought of as RAG?
A lot of the easy like plug and play RAG implementations is like plopping your documents through here in this input and then like you're kind of ready to go. Internally, the way it has to implement that is it is either going to take the user text and directly use that as a search against lexical or vector-based search engine, and it's going to take the results and dump that back in there. Or, and I think this is absolutely preferable at this point, it's going to take the context of the conversation and use that behind the scenes to make a tool call out to the document. So even if your implementation, it's not obvious that it's doing that, behind the scenes it has to be doing something that uses a tool call to actually get back at the documents. So it's still the same thing. It just, that's one of the reasons that I'm pretty uncomfortable with a lot of the frameworks is you should be able to tangibly grab those things and change them, but they're kind of hidden. You have to, back out what's really happening there.
You mind speaking a little bit about multi-agent systems and where do you see that going? It sounded from the conversation that we see agents still being very utilitarian, like, hey, we have a workflow or we have a specific task, rather than previous iterations of research which were all about, negotiation between agents representing specific goals.
Sure. This would be my hot take. I'm sure there's people that would disagree with it. Actually, I can soften the hot take a little bit. There is a paper, which I would have to track it down, but it was introduced like a week or so ago, that describes the failure modes of agentic frameworks that makes it where they are not hitting the quality thresholds of like workflows or single agent operators. And so I don't remember, I didn't actually read the paper or read the abstract. But so it is knowable the way they typically fail. My gut information getting into the hot take is that the models are getting smarter and smarter. So more capable of doing that type of stuff. But the nature of human language is still going to be human language. Like if I say, hey, do this thing, and it's just like a paragraph, what space of possibilities can satisfy that paragraph that aren't in the space that I really intended? And so when you say, give this idea to a bunch of models and they just self-negotiate, that's even more room to just kind of like diverge into this broader space of possibilities and not really get back to the thing that I want to do. And certainly, I'm not in the loop anymore, so I can't apply the corrective force. I remember some of I read the abstract and I read the first graphic. They did have information about like a lot of times it's a miscommunication. So like anytime you add more moving parts, you have more places for things to break. So they have situations where the orchestrating agent, which is kind of a piece of these things, is withholding information from the other ones. Or you have situations where the secondary agent hears it and is like, nah, screw you. I'm going to kind of do my own thing. And so it's just these things build up over time. I still think it's a really cool idea. One of 2 years ago paper was the first multi-agent thing I saw, where it's basically they had agents which represented like little characters inside a work environment. They had their own agendas and stuff to do, and you could like sit there and watch it like Sims, like jump around. But yeah, it's not generating useful information.
Sorry, you're right with the language model, because in previous iterations when we built it, it was all about rules and it was black and white. So I was kind of thinking about that as you were talking. Thank you.
When I see MCP, Model Context Protocol, is that just the tool gathering that you were kind of talking about, or is that like another frontier that is in the next chapter?
Yeah, that was, I can at least point at, hey, look at there. It's one of the ways that the technology is not getting smarter with MCP. We are getting more organized in the way that we allow things to interoperate. And full disclosure, I've yet to actually sit down and do MCP in anger. But effectively, it's a way of allowing everybody who has information that's useful outside themselves to say, like, here is my menu of options. If there's any really old school developers, do you remember SOAP for like communicating different protocols? How that work? These things actually appear to be working, where you can say, like, here's my advertised behaviors, use me as a tool call, and then you have the services understand the uniform way of gathering the context from all these different tools effectively on the internet. And so you can hook up calendars to travel apps to, it's just really neat way of combining everything in our ecosystem together. Let's go to this side. That's you, yeah, sorry.
Do you happen to know where we are with GraphRag?
Describe GraphRag, which is a hint that I'm gonna say, no, I don't really know.
It makes graphs out of documents, out of the contents of documents, and then uses that to help with retrieval.
Here, okay, so I already demonstrated my lack of knowledge here, but my intuition is RAG is not a thing, RAG's two things. And so one thing is you've got a tool that asks a graph about connected knowledge. And so, and the other side is you have the LLM that knows how to use the tool. So basically, you just put those two pieces together, and then that kind of implies, well, okay, where's the thing gonna break? Well, either it's going to ask the questions wrong, in which case it needs better information about how to navigate graphs and better examples, or the graph navigation is itself, the very mechanical old school stuff is not gonna be working as well as possible. I don't have any good specific examples.
That's helpful, actually.
Someone,
For one more question.
how do you keep updated on, latest developments?
Oh my gosh, I just like open the fire hose and like it's so hard. And like imposter syndrome right here, it's like everyone here knows so much more about some niche of this than I do. And all day I'm hearing like little bits and pieces of the stuff that's like, oh gosh, like MCP, graph. Yeah, we've already done two of them. I've got a few good email newsletters that are pretty hot. The small one works is great, and then I'll do a paper pile. Yeah, that's the graveyard for all the papers that I pretend I want to read. But that gives me a good stream of abstracts that I read. So that's nice. But not good. Sorry for accidentally ignoring this entire side of the room during the Q&A.
Thank you so much.
Thanks, guys.